Our entire observable universe was once smaller than an atom. This is the startling premise of cosmic inflation, the theory explaining the universe's explosive birth. By the end of this, you will understand the fundamental forces that shaped everything we see, from galaxies to the planets we call home. We will uncover why the cosmos looks so uniform and what mysterious energy could stretch space itself faster than light. What does it feel like to grasp the very first moments of existence? At that unimaginable instant, just a fraction of a second after everything began, the cosmos was a realm of pure chaos. The four fundamental forces we know today, gravity and electromagnetism, and the two nuclear forces, were fused into a single superforce. The laws of physics governing our reality had not yet taken shape. Within this seething, ultra-hot plasma, the story of our universe almost ended before it truly started. Scientists, piecing together the aftermath, were left with two profound mysteries etched into the fabric of the cosmos. The first is known as the horizon problem. If you look deep into space in one direction and then turn and look in the exact opposite direction, the universe looks remarkably the same. The temperature of the cosmic microwave background radiation, the faint afterglow of the Big Bang, is uniform to an astonishing degree, but according to the original Big Bang model, these distant regions should never have been in contact. There simply hadn't been enough time since the beginning for light or heat to travel between them and establish this equilibrium. It is as if you walked into a vast, crowded room where every single person, without having ever spoken, was wearing the exact same outfit and holding the exact same drink. How could such perfect coordination be possible? The second puzzle is the flatness problem. The geometry of our universe appears to be perfectly flat, balanced on a razor's edge. Think of space as a vast, flexible sheet. Matter and energy cause this sheet to curve. If there were too much density, the universe would have curved in on itself and collapsed in a big crunch long ago. If there were too little, it would have expanded so rapidly that galaxies and stars could never have formed. Our existence itself tells us the density was, and is, exquisitely fine-tuned. The question is, why? How did the universe achieve this perfect, stable balance? These two conundrums, the horizon problem and the flatness problem, were glaring flaws in the classic Big Bang story. They pointed to a missing chapter, a brief but transformative event in the universe's very first moments that could set everything right. This necessity for a new physics, for an event of unimaginable power, led directly to a radical and elegant solution proposed by one brilliant physicist. The answer arrived not from cosmology, but from the world of particle physics. In 1979, a young physicist named Alan Guth was working late at night, calculating the behavior of the very early universe. He was focused on grand unified theories, which attempt to describe how the fundamental forces were once merged. His calculations led him to a startling possibility. He realized that as the hot, young universe cooled, it might have undergone a phase transition, much like steam condensing into water. But in this cosmic case, the universe could have become supercooled, trapped in a state known as a false vacuum. This state possessed a remarkable property. Its energy density remained constant, acting like a form of anti-gravity. Unlike matter or radiation, whose gravitational pull slows expansion, this false vacuum energy generated a powerful repulsive force, causing space itself to stretch at an exponentially accelerating rate. Guth saw that this mechanism could solve the great puzzles in one elegant stroke. A tiny, subatomic patch of space, already uniform in temperature, could be inflated to a size larger than our entire observable universe, explaining the horizon problem. And the process would inevitably flatten the cosmic geometry, just as blowing up a balloon flattens the wrinkles on its surface, solving the flatness problem. He famously called this cosmic inflation a free lunch, a universe created from the gravitational energy of expansion itself, balanced by the negative pressure of the inflating field. His initial model, now called old inflation, proposed that the universe was stuck in this false vacuum state, expanding at a fantastic pace until it randomly tunneled out, like water suddenly freezing. The energy of that transition would then reheat the universe, filling it with the hot plasma of the standard Big Bang. Yet this brilliant idea had a critical flaw. The transition, the bubbles of true vacuum, would not merge smoothly. They would collide and create a chaotic, inhomogeneous mess, not the smooth universe we observe. This was the graceful exit problem. How could inflation stop everywhere at once without leaving the cosmos lumpy and broken? While Guth's original model was imperfect, its foundation was unshakable. It provided the first plausible mechanism for the universe's breathtaking transformation, a framework so powerful it would inspire a new generation of physicists to refine it. The challenge of the graceful exit demanded a more elegant solution. A few years after Alan Guth's groundbreaking proposal, other brilliant minds stepped in to refine the idea. Physicists like Andre Linde, Paul Steinhardt, and Andreas Albrecht proposed a new version of the theory, often called new inflation. Their critical insight was to replace the sudden, violent tunneling of the old model with a far more gentle and controlled process. They envisioned a hypothetical entity known as a scalar field, which they called the Inflaton field, permeating the infant cosmos. Think of this field as a ball resting high up on a gentle, sloping hill. This hill represents a state of high energy, the false vacuum that drives the explosive expansion. In the new model, this ball doesn't just fall off a cliff. Instead, it slowly, almost imperceptibly, rolls down the slope. As it rolls, the energy of the Inflaton field dominates the universe, forcing space to stretch at an exponential rate. This slow roll is the key to everything. It allows inflation to persist long enough to solve the horizon and flatness problems, and crucially, it provides that graceful exit. When the ball finally reaches the bottom of the hill, the field decays, releasing all of its stored energy in a tremendous blast that reheats the universe, creating the hot, dense soup of particles that marks the start of the conventional Big Bang. But the magic of the slow roll doesn't end there. As the Inflaton field rolls down, tiny quantum fluctuations, those inherent jitters that exist even in a vacuum, get stretched to enormous sizes. These minute ripples in energy became the seeds for all future structure in the cosmos. They are the primordial blueprints for galaxies, stars, and eventually, us. The slowness of the roll, measured by what scientists call slow roll parameters, became a powerful predictor. A very gentle roll would produce a specific pattern of density variations in the universe, while a steeper one would create a different pattern. This transformed cosmic inflation from a fascinating idea into a testable scientific theory. It now made concrete predictions about what we should see when we look at the oldest light in the universe. The question became, could we find the evidence to prove it happened? The search for proof began with a persistent, mysterious hiss. In 1964, two radio astronomers, Arno Penzias and Robert Wilson, were troubleshooting a massive horn antenna in New Jersey. They were plagued by a constant, faint microwave signal that came from every direction in the sky. It was not from our planet, not from our sun, and not even from our own galaxy. After painstakingly eliminating every possible source, including famously evicting a pair of pigeons and cleaning their droppings from the dish, the signal remained. They had inadvertently stumbled upon the oldest light in the universe, the cosmic microwave background. This was the cooled and stretched afterglow of the Big Bang's fireball, a snapshot of the cosmos when it was a mere 380,000 years old. This discovery was the smoking gun for a hot, dense beginning, but its true secrets were even more profound. The glow was astonishingly uniform, a near-perfect sea of microwaves. Yet when scientists looked closer, they found the crucial evidence inflation had predicted. The temperature was not perfectly even. Across the sky, there were minuscule variations, tiny ripples of hot and cold, only about 1 part in 100,000. That is like looking at a surface so smooth that the tallest mountains are no thicker than a sheet of paper laid on a football field. How could such incredible smoothness exist, punctuated by these specific, tiny flaws? Inflation provided the elegant answer. That initial subatomic patch was so small and interconnected that it easily achieved a uniform temperature. The violent expansion then stretched this smoothness across the entire sky. And those tiny fluctuations, they are the amplified quantum jitters from the Inflaton field, the primordial seeds that gravity would later sculpt into the vast cosmic web of galaxies. To read this ancient code, we launched eyes into space. Satellite missions like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck spacecraft have mapped these temperature variations in exquisite, beautiful detail. Their all-sky maps look like a cosmic eggshell, speckled with hot and cold spots of specific sizes. This pattern, known as the power spectrum, is the Rosetta Stone of cosmology. It does not just tell us the universe is lumpy, it tells us exactly how lumpy it is on different scales, and that pattern is a perfect match for what the simplest models of inflation predict. The characteristics of these spots, their size and distribution, encode the universe's vital statistics, its age, composition, and most importantly, its initial conditions. This cosmic fossil does not merely confirm the universe had a hot beginning. Its intricate details bear the unmistakable fingerprint of an inflationary growth spurt. But what does the specific language of this fossil actually say? These subtle temperature ripples are a cosmic fossil of the quantum world. The universe we see, with its vast galactic voids and brilliant clusters, began as subatomic tremors. During inflation's furious expansion, the tiny quantum jitters in the Inflaton field were stretched across the cosmos, frozen into the fabric of space as minute differences in density. Where the field was slightly more energetic, a bit more matter would eventually coalesce over billions of years into a galaxy. Where it was slightly less, a vast cosmic void would form. The pattern we see in the cosmic microwave background is the direct imprint of these quantum seeds, blown up to a scale beyond comprehension. Inflation made a specific prediction about this pattern. It suggested the fluctuations should be nearly scale invariant. This means that whether you look at a patch of sky the size of a single galaxy or a supercluster, the relative strength of the hot and cold spots should be almost identical. It is the cosmic equivalent of a coastline looking similarly rugged whether you view it from an airplane or a satellite. This idea, formalized as the Harrison-Zeldovich spectrum, was a bold theoretical forecast. The degree to which the real universe deviates from perfect scale invariance is measured by a number called the spectral index. A value of 1 would mean perfect scale invariance, but inflation models predicted a value slightly less than 1, meaning the universe is a tiny bit smoother on the largest scales. When scientists measured it, the observed spectral index matched the inflationary prediction with stunning precision. But the story gets even richer when we listen to the harmonics of this primordial whisper. The early universe was a seething plasma, a dense soup of particles and light. gravity tried to pull matter together into clumps while the intense pressure of radiation pushed it apart. This created oscillations, cosmic sound waves rippling through the fiery medium. When the universe cooled enough for atoms to form, releasing the cosmic microwave background, these waves were instantly frozen in place. We see them today as a specific pattern of rings in the sky, a series of acoustic peaks in the power spectrum. The precise size and height of these peaks are a treasure trove of information. The first peak tells us the universe is geometrically flat. The second reveals the density of ordinary matter. The third confirms the amount of dark matter. This frozen music is a direct recording of the universe's composition and its gravitational history. These anisotropies are more than just a map of the infant cosmos. They are a direct link to the quantum nature of gravity itself. The fluctuations we observe are thought to include a component from primordial gravitational waves, ripples in spacetime generated during inflation. Finding their specific signature would be the ultimate confirmation, allowing us to peer directly into that first, unimaginable fraction of a second. Every galaxy, every star, every planet exists because of a quantum tremor that was amplified to cosmic proportions. This raises a profound question about the very beginning. What could have sparked such a monumental event, and what does it mean for the ultimate fate of our entire cosmos? The empty void of the early universe was not a placid sea. Deep within that subatomic realm, a quantum storm was raging. A principle of quantum mechanics tells us that a perfect vacuum is impossible, that empty space itself is a seething foam where pairs of virtual particles and antiparticles constantly pop into existence, borrowing energy from the void for an immeasurably brief moment before annihilating each other and vanishing. This relentless jittering is the fundamental nature of reality at its smallest scale. When cosmic inflation began, it seized upon this intrinsic chaos. The quantum fluctuations in the Inflaton field, those probabilistic ripples in energy that were once confined to a microscopic domain, were caught in the act of expansion. As space stretched faster than light, these tiny tremors were stretched along with it, magnified from the quantum world to the cosmic stage. They were no longer fleeting probabilities. They were frozen into place as permanent, classical imprints on the universe. This quantum-to-classical transition is the crucial step where the roll of a quantum dice became the fixed, deterministic blueprint for everything to come. A fluctuation that was once a mere possibility became an actual, tangible region of slightly higher or lower density, a seed around which gravity could work for billions of years. The amplitude of these fluctuations, the strength of those hot and cold spots we see in the cosmic microwave background, is not arbitrary. It is a direct measure of the incredible power driving the inflationary expansion. The energy scale required to produce the patterns we observe is almost beyond belief, around 10 to the 16 billion electron volts. This places the engine of inflation tantalizingly close to the theoretical grand unification energy, the scale where three of the fundamental forces, electromagnetism and the strong and weak nuclear forces, are thought to merge into one. This is one of the most staggering insights of the entire theory. It forges a direct, unbreakable link between the unpredictable quantum realm and the majestic architecture of the cosmos. The grand tapestry of superclusters and voids, the entire large-scale structure of the universe, finds its ultimate origin in the tiniest, most fundamental jitters of space-time. This quantum genesis, however, leaves us facing a monumental mystery. What was the Inflaton field itself, this enigmatic entity that sculpted our reality, and is there any way we could ever detect its echo? The Inflaton field remains a ghost in the cosmic machine. We can see its breathtaking effects, we can trace its fingerprints across the sky, yet its fundamental identity is a profound mystery. This hypothetical scalar field is the protagonist of our origin story, the engine of cosmic inflation. But what is it made of? Unlike the Higgs field, which endows particles with mass, the inflaton's role was to dominate the energy density of the universe and drive its exponential expansion. It was a temporary but monumental force, a sculptor that shaped the cosmos and then vanished without a trace. Scientists have proposed a gallery of candidates, each with its own unique signature. In the complex landscape of string theory, the inflaton could be a moduli field representing the shape and size of hidden extra dimensions. In theories of supersymmetry, it might be a superpartner of a known particle, a shadowy twin waiting to be discovered. Each candidate field possesses a distinct potential energy landscape, an imaginary hill or valley that dictates how it behaves. A steep slope leads to a short, violent burst of inflation, while a long, gentle plateau produces the slow roll that creates our vast, smooth universe. The specific properties of this field, its mass and how it interacts with other particles, are not just abstract numbers. They are the dials that set the duration of inflation, the strength of the quantum fluctuations that became galaxies, and the incredible heat of the reheating phase that birthed the Big Bang's fireball. This search for the inflaton's identity forces us to confront even grander possibilities. Could this field, which jump-started everything, be related to the dark energy that now accelerates the universe's expansion? Some theories suggest they might be different manifestations of a single, underlying substance, a cosmic thread connecting the beginning to the end. Finding the inflaton would do more than complete a chapter in our history. It could reveal a deeper unity in the laws of physics, linking the universe's most explosive moment to its long-term fate. The hunt for this elusive entity is now a primary driver of both theoretical and experimental physics. Next-generation telescopes and satellite missions are designed to measure the cosmic microwave background with even greater precision, searching for subtle twists in the polarization of that ancient light that could betray the inflaton's specific signature. Particle accelerators, by probing ever higher energies, hope to recreate conditions that might reveal fields behaving like the inflaton. We are chasing a shadow, but one whose outline is becoming clearer with every observation. Yet for all its success, the theory of cosmic inflation is not without its rivals, and compelling alternative explanations are waiting in the wings. Yet for all its elegance, cosmic inflation is not the only story on the table. Competing narratives challenge this dominant paradigm, each offering a radically different vision of the cosmos's first moments. One of the most compelling is the cyclic model, conceived by physicists Paul Steinhardt and Neil Turok. This theory does away with a single beginning altogether. Instead, it proposes an endless, rhythmic dance of creation. Our universe exists on a vast, multidimensional membrane or brain, floating in a higher dimensional reality. In this model, the Big Bang is not a singular birth from nothing, but a periodic event triggered when our brain collides with a neighboring one. Each collision injects immense energy, heating the universe and beginning a new cycle of expansion. The universe expands, cools, and forms galaxies, but dark energy eventually causes the expansion to accelerate, diluting the cosmos to an almost empty state, setting the stage for the next collision and a new beginning. This endless cycle solves the horizon and flatness problems not through a one-time stretch, but through the repeated smoothing and resetting over trillions of years. Another path is the bouncing cosmology. Imagine the universe not as a single explosive birth, but as a great cosmic heartbeat. In this scenario, a previous phase of the universe contracts under its own gravity, growing hotter and denser. Instead of collapsing into a singularity of infinite density, quantum gravity effects take over at the smallest possible scale, causing a rebound. The universe bounces back, entering the expansion phase we observe today. This bounce naturally produces a large, smooth, and flat universe without requiring a separate inflationary epoch, as the intense compression and subsequent release iron out any prior wrinkles. Other ideas, like string gas cosmology, suggest that the early universe was a hot, dense gas of the fundamental strings predicted by string theory. The interactions and winding modes of these strings could have naturally prevented the universe from becoming too irregular, leading directly to the homogeneity and flatness we see. Similarly, emergent universe scenarios picture a cosmos that was always there, existing in a near-static state for an eternity before slowly transitioning into the expanding phase we inhabit. Each of these alternatives presents a unique solution, but none are perfect. They struggle to match the precise, quantitative predictions of inflation, particularly the specific pattern of fluctuations seen in the cosmic microwave background. The cyclic model, for instance, must explain how the violent collision of branes produces a universe as serene and uniform as our own. Bouncing cosmologies must navigate the unknown physics of the quantum bounce itself. Yet their existence is vital. They force cosmologists to question every assumption and refine every prediction. The true power of inflation is not that it is the only idea, but that it is the one that has so far survived the most brutal experimental scrutiny. This competitive landscape sets the stage for the ultimate test. A prediction so profound its confirmation would be a direct message from the universe's violent birth. A ghostly sea of ripples flows through the cosmos, an echo of creation's first violent shudders. These are primordial gravitational waves, predicted by inflation as its ultimate signature. During that explosive expansion, the theory says that quantum fluctuations were not just in the Inflaton field, but in the very fabric of spacetime itself. The gravitational field, the metric that defines distances and time, was also jittering with probabilistic tremors. Inflation seized these tiny ripples and stretched them, magnifying them from the quantum foam into literal waves in the geometry of the universe. Unlike the gravitational waves we detect from colliding black holes, which are specific events, this would be a continuous background hum, a fossil from the universe's first fraction of a second. The challenge is finding this whisper beneath the roar of everything that has happened since. The most promising place to look is in the oldest light we have. These primordial gravitational waves would have left a unique scar on the cosmic microwave background. As the waves passed through the hot plasma of the early universe, they would have gently sheared the light, imparting a specific curling pattern to its polarization. Scientists call this distinctive fingerprint B-mode polarization. Think of the CMB light as a field of waves, each with a specific orientation. The normal density variations create a simpler, radial pattern like petals on a flower. But the signature of gravitational waves is a swirling, vortex-like pattern, like the curls in a fingerprint. Finding this specific curl in the polarization of the ancient sky would be the smoking gun, the direct evidence that spacetime itself was once shaking violently. The hunt for this cosmic fingerprint has become one of the great quests of modern science. High on the Antarctic plateau, where the air is thin and dry, telescopes like BICEP and the Keck array stare at a pristine patch of sky year after year, searching for this faint signal. The pursuit reached a fever pitch in 2014 when the BICEP-2 team announced a thrilling discovery. They believed they had found the telltale B-modes, a detection that promised a Nobel Prize and seemed to confirm inflation at an energy scale near grand unification. The scientific world held its breath, but further analysis incorporating data from the Planck satellite revealed a cruel cosmic mimic. The signal they saw was largely due to interstellar dust within our own galaxy, dust that can produce a very similar swirling pattern. It was a sobering lesson in the painstaking care required for such a delicate measurement. This setback did not end the search, it refined it. The key measurement is a number known as the tensor to scalar ratio, denoted by the letter R. This ratio compares the strength of these gravitational wave ripples, the tensor fluctuations, to the strength of the density ripples, the scalar fluctuations that seeded galaxies. It is a single number that holds immense power. A detection of R, even a very small one, would immediately tell us the incredible energy scale at which inflation occurred. A large value would point to a violent, high-energy process, while a smaller, more elusive signal would suggest a gentler, lower-energy inflation. This number is so crucial that a new generation of experiments is being built to find it. Space-based observatories like LightBird are being designed to scan the entire sky from above Earth's atmosphere, free from the confounding effects of dust and water vapor, offering our cleanest possible view. Detecting these primordial ripples would do more than just confirm inflation. It would tear open a window to an era that is otherwise completely inaccessible, the Planck epoch. This was the first fleeting moment after the Big Bang, a time when the universe was so incredibly dense and hot that the classical theory of gravity breaks down and quantum effects must have ruled the cosmos. These gravitational waves would have been generated when the universe was governed by quantum gravity, a theory we still do not possess. They would carry direct information about physics at energies 1 trillion times higher than what our most powerful particle colliders can reach. It would be like receiving a message from the very edge of physical law, a data stream from the moment when time itself may have found its meaning. The pursuit continues, a testament to our deep desire to understand not just how the universe is, but how it began to be. Our cosmic story does not end with a single universe. The same mechanism that solved our greatest cosmological puzzles may have spawned a reality of unimaginable scope, a multiverse. The concept emerges from a variation known as eternal inflation. Picture our universe not as a unique event, but as one single bubble in a vast, frothing cosmic sea. In this scenario, the overall process of inflation never truly stops. The repulsive energy of the Inflaton field continues to drive an explosive expansion of the meta-universe, the background space, forever. However, quantum fluctuations cause different patches of this inflating background to randomly decay. In one region, the Inflaton field might roll down its energy hill, ending inflation and creating a hot Big Bang universe, a stable bubble like our own. But in the space between these bubbles, inflation rages on, constantly creating new territory where more bubbles can form. Each of these pocket universes could have its own unique properties, born from the random value of the Inflaton field when it decayed. This value determines the physical constants within that bubble, the strength of gravity, the mass of an electron, the very laws of physics as we know them. Most of these universes would be stillborn, chaotic realms where atoms never form or forces are too weak to build structure. We, quite simply, could only arise in one of the rare, finely tuned bubbles where the constants allow for galaxies, stars, planets, and life. This idea is both profound and deeply controversial. For proponents like Leonard Susskind, the multiverse is a natural, almost inevitable consequence of the physics of inflation. It offers an explanation for the puzzling fine-tuning of our own cosmos, suggesting that while a life-permitting universe is incredibly rare, it was inevitable in a sufficiently vast and varied ensemble. Yet for critics like Paul Steinhardt, this very vastness is the problem. If anything that can happen will happen in some universe, then the theory loses its predictive power. How can we test a concept that posits an infinite number of unobservable realms? This pushes cosmology to its philosophical limits, forcing us to ask what makes a scientific theory truly scientific. Is the multiverse a breathtaking insight into the nature of reality, or a step into untestable metaphysics? This speculative frontier reminds us that our quest to understand the beginning is also a search for the ultimate context of our existence. Our journey now takes us back to the very first moment to confront the most daunting mystery of all, the initial singularity that inflation was meant to erase. The infinite density of the Big Bang singularity is a sign that our physics has failed. It marks a boundary where time and space, as we understand them, simply cease to exist. Cosmic inflation offers a profound escape from this dead end. It erases the need for a singular starting point by providing a prelude, a phase of exponential expansion that could have sprung from something far more stable. This idea was taken to its ultimate conclusion by physicists James Hartle and Stephen Hawking with their no-boundary proposal. They suggested that if we could rewind the cosmos to its very beginning, we would not find a sharp, singular edge. Instead, the fabric of spacetime would become smooth and finite, like the rounded tip of an egg. In this quantum picture, the distinction between time and space blurs, and the universe simply has no initial boundary, no moment of creation from nothing. It just is. Inflation fits seamlessly into this framework, acting as the mechanism that takes this smooth, finite quantum beginning and blows it up into the vast, classical universe we inhabit. Another possibility is that our entire cosmos is the result of a quantum fluctuation. In the endless churn of a primordial meta-universe or a timeless vacuum, a bubble of space-time could have spontaneously tunneled into existence, much like an electron appearing on the wrong side of a barrier it cannot classically cross. This nascent universe would have been tiny, perhaps only a billionth the size of a proton, but if it was born in the right high-energy state, the Inflaton field would have immediately taken over, inflating that quantum spark into a cosmic panorama. While these ideas push the question of an absolute beginning into the realm of quantum gravity, they do not necessarily provide a final answer. Has the universe always existed in some form, or did it truly begin at a point? Inflation makes the question more subtle, but it does not make it disappear. It transforms a crisis of infinite density into a profound puzzle about the nature of time and existence itself. This leads us to a final, breathtaking consideration, connecting the universe's explosive birth to its long-term destiny. The universe remained a cold, empty void during its explosive inflation, a cosmic landscape stretched thin and silent. All the energy that would later forge galaxies and stars was locked away, trapped within the Inflaton field itself. Then, in an instant, everything changed. As the Inflaton field reached the bottom of its energy hill, it did not simply stop. It began to oscillate, wobbling wildly around its lowest energy point like a ball bouncing at the bottom of a bowl. This frantic, chaotic shaking was the trigger for a cosmic rebirth. The energy stored in the field's oscillations had to go somewhere, and it was transferred violently into the creation of the universe's first fundamental particles. This pivotal moment is called reheating, the event that ignited the hot Big Bang. Think of it as a billion power plants switching on at once, flooding the sterile, inflated cosmos with a raging fireball of quarks, electrons, and photons. The temperature skyrocketed in a flash from near absolute zero to an almost inconceivable 10 to 15 billion degrees Kelvin, a heat so intense it defies any earthly comparison. This was not a gentle warming, but a furious resurrection of the cosmos. The mechanism of this decay was profoundly complex. In some models, the Inflaton field decayed perturbatively, shedding its energy particle by particle, like a spinning top gradually slowing down. In more dramatic scenarios, a process called parametric resonance occurred, where the field's oscillations matched a natural frequency of the quantum vacuum, causing an explosive, resonant production of particles. It was a cosmic feedback loop of immense power, rapidly filling the universe with the raw ingredients for everything to come. The efficiency of this process was everything. It set the initial temperature for the hot Big Bang and determined how many of which particles were created. The specific physics of reheating could have dictated the abundance of mysterious relics like dark matter, whose particles may have been forged in this initial inferno. The violent turbulence of this transition might even have generated a secondary background of gravitational waves, a faint hiss layered over the primordial signal from inflation itself. This moment of cosmic transmutation, where a field's potential energy became tangible matter and radiation, marks the true beginning of the universe as we recognize it. From this point forward, the story shifts from the creation of space itself to the formation of everything within it. The quantum seeds sown during inflation did not remain as faint whispers in the cosmic background. They were the genetic code for the entire visible universe, the primordial instructions for building a cosmic web of staggering complexity. Those microscopic overdensities, regions where the density was just a fraction of a percent higher than average, were the universe's only building blocks. For hundreds of millions of years, gravity was the silent, patient sculptor. It gently pulled matter toward these slight density enhancements in a process known as linear growth. The overdense regions slowly became denser, while the underdense regions emptied out further, carving the first vast voids into the expanding cosmos. This was a stately, predictable dance where every ripple grew in proportion to its initial size. But gravity is a runaway process. Once a region gathers enough mass, its gravitational pull becomes self-reinforcing, and the growth turns non-linear. The careful, linear progression shatters. Matter collapses catastrophically, not gradually, into dense knots. Dark matter, which feels gravity but not light pressure, formed an invisible scaffolding first. Ordinary matter, primarily hydrogen and helium gas, then flowed into these gravitational wells, clumping and condensing until the pressure and temperature at their cores ignited the first nuclear furnaces. The universe, dark for so long, blazed with the light of its first stars. We can watch this entire cosmic drama unfold inside a supercomputer. N-body simulations, which model the gravitational interactions of millions or even billions of particles, are our time machines. We can input the initial conditions left by inflation, a nearly Gaussian random field of fluctuations, and let the simulation run. The result is breathtaking. From a smooth, almost featureless sea of particles, an intricate filamentary structure emerges, a vast cosmic web of dark matter halos connected by delicate threads, with enormous empty voids in between. This is the large-scale structure of our universe, and it matches the maps we create with powerful telescopes. The fact that this simulated web, born from inflationary seeds, so perfectly mirrors the real one observed by projects like the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument is a monumental triumph for the theory. It tells us that the specific statistical properties of those initial ripples, their Gaussian distribution where positive and negative fluctuations are symmetrically likely, are written into the very architecture of the cosmos. Yet scientists are hunting for tiny cracks in this Gaussian perfection, subtle deviations known as non-Gaussianity. These would appear as unexpected correlations between fluctuations, a statistical skew that could reveal how the Inflaton field interacted with itself or with other fields. Finding this signature would be like moving from a blueprint of a building to the architect's personal diary, offering a direct glimpse into the dynamics of the inflationary engine itself. Every galaxy cluster, every solitary star, and every dark cosmic void is a direct descendant of a quantum tremor. This profound connection, from the subatomic jitter to the galactic supercluster, stands as one of the most compelling arguments for our cosmic origin story. The next generation of observatories will read this cosmic genealogy with even greater precision, searching for the final clues written into the largest structures in existence. The search for Inflation's final proof is accelerating into a new era of cosmic discovery. A suite of next-generation observatories, both on the ground and in space, is being built to listen for the universe's faintest whispers with a clarity we have never before possessed. High on the dry Chilean desert plateau, the Simons Observatory is rising, a collection of telescopes so sensitive they will map the cosmic microwave background with a resolution 50 times greater than the Planck satellite. Its successor, an even more ambitious project known as CMB Stage 4, or CMB-S4, will deploy 500,000 superconducting detectors across 2 continents, in the Chilean Andes and at the South Pole. This colossal effort is designed to achieve one primary goal: to hunt for the elusive B-mode polarization, the swirling fingerprint of primordial gravitational waves, or to prove it is fainter than anyone predicted. They will measure the spectral index, the slight deviation from perfect scale invariance, with such precision that it will act like a cosmic barcode scanner, ruling out entire families of inflationary models and pointing toward the one true potential energy landscape of the Inflaton field. But the hunt will not rely on light alone. The Laser Interferometer Space Antenna, or LISA, is a planned space-based observatory that will open an entirely new sense. While ground-based detectors like LIGO listen for the loud, low-frequency chirps of colliding black holes, LISA will be tuned to a much quieter, lower-frequency hum. It will detect gravitational waves with wavelengths so long they span entire solar systems. This stochastic gravitational wave background is a constant sea of ripples, and within its hiss could be a contribution from the violent end of inflation itself, from the turbulent reheating phase when the universe was reborn in a fireball of particles. Imagine listening to the cosmos not with your ears, but with your entire body, feeling the subtle, constant stretching and squeezing of space itself. A third, revolutionary probe will peer into the cosmic dark ages. Before the first stars ignited, the universe was filled with a fog of neutral hydrogen gas. This gas absorbs and emits light at a very specific 21-centimeter wavelength. Next-generation radio arrays, like the hydrogen epoch of reionization array and the future square-kilometer array, will attempt to map this primordial hydrogen, creating a 3-dimensional tomographic image of the infant cosmos. This 21-centimeter signal is a direct tracer of the density fluctuations sown by inflation, offering an independent and incredibly detailed map of the primordial seeds. By comparing this map to the one from the CMB, scientists can perform a cosmic cross-check, verifying if the same process that created the hot and cold spots also sculpted the distribution of the first atoms. The synergy of these different probes, the ancient light of the CMB, the gentle ripples in space-time, and the large-scale structure of the universe will weave a complete and consistent story. They will either confirm our inflationary paradigm in stunning detail or force us to tear it down and start anew. The data flowing in over the next decade will act as a guide, leading theorists through the labyrinth of possible models toward a final, complete theory of the universe's first moment. We are on the cusp of turning a compelling idea into a definitively known chapter of cosmic history, a golden age where the invisible becomes tangible and the quantum past speaks directly to us. The universe has accelerated its expansion not once but twice, The first burst, cosmic inflation, was a violent, short-lived event that forged the cosmos. The second, driven by dark energy, is a gentle, persistent push shaping our future. Could these two accelerations be different faces of the same fundamental force? They operate on opposite ends of time, inflation in the first sliver of a second and dark energy dominating today, billions of years later. Their energy scales are incomprehensibly different. The energy density that drove inflation was staggeringly high, while dark energy is incredibly feeble, a ghost of its primordial counterpart. Yet the underlying mechanism, a form of energy inherent to space itself that generates repulsive gravity, is hauntingly similar. This parallel has led physicists to wonder if dark energy is a faint echo of the Inflaton field, a remnant that never completely faded away. Perhaps the field that powered the Big Bang's prelude simply settled into a much lower energy state, and that latent energy is what we now measure as the cosmological constant. This is the simplest model for dark energy, a constant, unchanging energy density woven into the vacuum of space. But this simplicity brings its own profound puzzles, namely why its observed value is so unimaginably small compared to theoretical predictions. This discrepancy is one of the greatest unsolved problems in physics. Other, more dynamic ideas exist. One compelling candidate is called quintessence. Imagine a cosmic cousin to the Inflaton field, a scalar field that is slowly evolving even today. Unlike the cosmological constant, quintessence is not static. Its energy density can change over time, gradually rolling down its own potential energy slope. In this model, dark energy is not a leftover constant but an active, if sluggish, phase of the universe, a late-time inflation operating at a snail's pace. This blurs the line between the two accelerations, suggesting the universe might be capable of multiple inflationary phases, each with a different character and purpose. The search for a connection is more than theoretical curiosity. If dark energy is dynamic like quintessence, then the ultimate fate of the cosmos changes dramatically. A cosmological constant leads to a perpetual, ever-accelerating expansion, but a quintessence field could eventually decay, potentially leading to a different end or even a new beginning. We are now hunting for tiny variations in the expansion rate over billions of years, looking for any sign that dark energy is not a constant but an evolving entity. Finding such a signature would forge a direct link between the universe's birth and its death, revealing that the same physics that set the stage for our existence is also writing its final act. This quest forces us to confront the deepest nature of reality, asking if the cosmos is governed by a single, recurring theme. Our universe feels perfectly tailored for life, but this fine-tuning might be the ultimate cosmic coincidence. The strength of gravity, the mass of an electron, the value of the cosmological constant, each of these fundamental numbers appears to be set with incredible precision. If gravity were slightly stronger, the universe would have collapsed long ago. If the cosmological constant were a little larger, space would have ripped itself apart before stars could form. How do we explain this breathtaking balance? One provocative answer lies in the marriage of inflation and the Anthropic Principle. If cosmic inflation is eternal, spawning an infinite multiverse of bubble universes, then every possible set of physical constants will be realized somewhere. In the overwhelming majority of these universes, the constants will be wrong for life. Stars will not ignite, atoms will not bond, and cosmic history will be brief and barren. But in a rare, infinitesimal fraction of the multiverse, the numbers will, by pure chance, line up correctly. In those exceptional bubbles, beings can evolve to look back and wonder at their own existence. We are not special, we are simply lucky, living in one of the few places where the local laws of physics allow for observers. This idea transforms the question of why our universe is fine-tuned. It stops being a mystery of design and becomes a simple question of selection bias. We could not possibly find ourselves in a universe incapable of hosting us. For proponents, this is a powerful and elegant explanation, a natural consequence of the inflationary framework that removes the need for a deeper reason. Yet for many scientists, this is a deeply unsatisfying surrender. Critics argue that the Anthropic Principle effectively gives up on the dream of fundamental physics, which is to derive the constants of nature from a unique predictive theory. If anything that can happen does happen in some universe, then have we explained anything at all, or have we just shifted the mystery to an unobservable and infinite arena? This debate forces us to confront the very nature of scientific explanation. Are some facts, like the values of our constants, simply brute, contingent truths with no deeper cause? Or must a final theory account for everything we see? The Anthropic Principle, born from the logic of inflation, pushes cosmology into the realm of philosophy, challenging us to define what a good explanation actually is and forcing us to wonder if our quest for a single, elegant theory of everything is a search for a phantom. Even our most successful cosmic stories run up against the edge of the known. For all its explanatory power, inflation itself requires a starting point it cannot provide. Why was the Inflaton field positioned perfectly on that high-energy hill, poised to roll and trigger the entire cosmic chain of events? This is the initial conditions problem, the theory's own version of the question it was meant to solve for the Big Bang. Inflation elegantly erases the need for a finely tuned beginning for the hot universe, but it demands a finely tuned beginning for itself. We are left chasing the ultimate cause, a regress that pushes our explanations back toward an even more mysterious genesis. The theory also operates within the comfortable realm of classical physics, treating spacetime as a smooth, continuous fabric. But this picture must shatter when we rewind to the first fleeting moments. At the Planck scale, a time of 10 to the negative 43 seconds, the universe was so incredibly dense that the very concepts of space and distance lose their meaning. Here, quantum gravity must reign, a theory that successfully merges the large-scale rules of general relativity with the probabilistic weirdness of the quantum world. We do not yet possess this final theory. Consequently, our description of inflation's very onset is provisional. It sketches a magnificent portrait of cosmic expansion, but the first brushstrokes applied at the Planck epoch are blurry and undefined, awaiting a deeper canvas. This conceptual frontier becomes even more bewildering when we confront the multiverse. If eternal inflation is correct, spawning an infinite array of bubble universes, we face the profound measure problem. How do we calculate probabilities in an infinite ensemble? If every possible outcome occurs in an infinite number of universes, then talking about what is likely or unlikely seems to lose all meaning. How do we determine that our universe is rare if an infinite number of copies of it also exist? This is not just a philosophical puzzle, it is a mathematical crisis that challenges our ability to make any testable predictions from the multiverse hypothesis. Without a way to measure the infinite, the concept risks floating beyond the reach of science. These boundaries are not failures, they are essential guideposts. They tell us that cosmic inflation is likely what physicists call an effective theory. It is a powerful and remarkably accurate description of the universe within a specific domain, from a fraction of a second after the Planck time onward. But it is not the final word. It points toward a more fundamental framework, a theory of quantum gravity that can describe the true nature of spacetime at its smallest possible scale. This quest now leads us beyond the inflationary paradigm, into the realm where the fabric of reality is woven from threads we are only beginning to understand. String theory dares to ask what happens when the universe was smaller than the smallest particle. This leading candidate for a theory of quantum gravity replaces the idea of point-like particles with tiny, vibrating loops of energy. In this framework, the fundamental constituents of reality are these strings, and their different vibrational patterns give rise to all the forces and particles we observe. This elegant idea naturally provides a playground for cosmic inflation, offering concrete mechanisms born from its own mathematical structure. One compelling scenario is brane inflation. Our entire universe could be a three-dimensional membrane or brane existing within a higher dimensional reality. Inflation in this picture could be sparked by the motion of two such branes as they move toward each other in the hidden bulk dimensions. The energy of their interaction drives the exponential expansion of our own brane space. Another critical piece is moduli stabilization. String theory requires extra spatial dimensions, which are curled up into a complex microscopic shape. The properties of this shape are described by fields called moduli. For our universe to be stable, these moduli must settle into specific values, a process that can naturally produce the kind of energy landscape needed to power a slow roll inflation. Scientists have built detailed models on these foundations. The KKLMMT model, for instance, is a specific realization of brane inflation. It places our brane in a warped throat, a region of space where gravity causes a steep curvature, much like a funnel. This warping creates the gentle slope needed for the Inflaton field to roll slowly, solving a major theoretical headache known as the eta problem. This problem asks why the mass of the Inflaton field remained so incredibly small, allowing inflation to persist. In the warped geometry of string theory, the intense gravitational red shift in such a throat can naturally suppress the field's mass, providing the graceful, prolonged expansion that our universe required. Beyond explaining a single inflationary event, string theory provides perhaps the most natural home for the multiverse. The number of possible ways to curl up the extra dimensions is astronomically large, perhaps around 10 to the 500. Each distinct configuration corresponds to a different vacuum state with its own unique physical laws and constants. This is the string landscape, a vast cosmic catalog of possible universes. Our universe, with its specific particle masses and force strengths, would be just one tiny entry in this nearly infinite directory, realized in one bubble among countless others. The great challenge, of course, is testing these profound ideas. String theory operates at energy scales far beyond the reach of any particle accelerator. Yet, its union with inflation is a hotbed of theoretical innovation. The specific dynamics of brane collisions or moduli decay could imprint unique signatures in the cosmic microwave background, perhaps as specific patterns of non-Gaussianity or a characteristic spectrum of gravitational waves. Finding such a fingerprint would be a monumental step, not just confirming inflation but pointing directly toward the unified physics of strings. This quest to marry the universe's largest phenomenon with its smallest theoretical building blocks is pushing the very boundaries of human knowledge, suggesting that the answer to how everything began may be written in the vibrations of the cosmos's most fundamental strings. The smooth fabric of spacetime dissolves into a swirling quantum foam at the very smallest scales. Loop quantum gravity proposes that space itself is not continuous, but woven from finite, discrete loops, a tapestry of individual threads. This radical reimagining of reality's foundation leads to a dramatic new origin story for the cosmos, known as loop quantum cosmology. In this picture, the Big Bang was not a violent beginning from nothing, but a monumental transition, a big bounce. Our expanding universe could have been preceded by a vast, ancient cosmos that contracted under its own gravity. Instead of collapsing into an infinitely dense point, the repulsive force generated by the quantum geometry of space itself caused the universe to rebound like a cosmic spring coiling and then releasing with immense force. This bounce naturally provides the clean, smooth, and flat initial conditions that inflation requires, solving the problem of what came before. How does this quantum structure alter the universe's expansion? The classic equations that describe cosmic evolution, the Friedmann equations, break down at the singularity. Loop quantum cosmology modifies these equations at the highest densities, introducing a powerful repulsive term born from the graininess of space. This quantum pressure becomes so immense that it halts the collapse and drives a phase of superinflation, an incredibly brief and explosive expansion that occurs even before the Inflaton field begins its slow roll. This superinflation naturally sets the stage, positioning the Inflaton field on its high-energy hill and providing the kickstart for the subsequent, longer inflationary epoch we have discussed. The Inflaton field is no longer a mysterious actor entering an empty stage, but a character whose entrance is directed by the quantum gravitational scenery itself. This interplay elegantly resolves the initial condition problem of inflation, suggesting its origin lies not in a random fluctuation, but in the fundamental, non-singular physics of a bouncing universe. While still a developing theory, loop quantum cosmology presents a powerful and compelling alternative to string theory in the quest to unify gravity and the quantum world. It offers a complete, self-contained narrative that begins with a bounce and flows directly into the formation of our universe, all governed by the discrete geometry of space. This quantum gravitational perspective profoundly enriches our story, but it also forces us to reconsider one of our most fundamental concepts. If space has a quantum structure, what does that imply for the nature of time itself? The universe began in a state of profound, almost impossible order. This is the puzzle of low entropy, a concept tied to the second law of thermodynamics which dictates that disorder or entropy always increases. This relentless rise gives us the arrow of time, the reason we remember the past but not the future, why ice melts in a warm room but never spontaneously refreezes. Yet the early cosmos presents a baffling contradiction. The hot, dense plasma of the Big Bang was a state of exceptionally low entropy, a perfectly smooth and ordered starting point from which everything could only become more chaotic. Why would the universe begin in such a pristine, organized condition? Cosmic inflation offers a powerful resolution by pushing the ultimate low entropy state even further back in time. The initial patch that inflated was unimaginably smaller and more uniform than the Big Bang fireball, a speck of cosmic perfection. The act of inflation itself then generated a colossal amount of entropy. Those quantum fluctuations in the Inflaton field, stretched to cosmic sizes, became a vast tapestry of density variations. The production of primordial gravitational waves added another layer of complexity and disorder. In essence, inflation took a tiny, ordered seed and used it to manufacture the immense disorder that the second law of thermodynamics requires to function, effectively winding up the universe's clock and setting time on its irreversible forward march. Not all physicists agree on this origin story. Roger Penrose, for instance, proposed a radically different vision called conformal cyclic cosmology. He suggests that our universe is just one eon in an endless cycle. In the far, far future, the universe expands into an utterly empty, featureless state. Stripped of all scale, this endless void becomes mathematically identical to the Big Bang's singularity, a state of low entropy ready to rebound into a new eon. In this breathtaking view, the arrow of time is reset with each cycle, and the low entropy beginning is not a one-time miracle but a recurring phase in an eternal return. This deep connection between inflation and thermodynamics hints at something even more fundamental: the process of stretching quantum fluctuations into classical, determinate seeds may be intimately linked to the very emergence of time from a timeless quantum realm. Before inflation, in the Planck epoch, the distinction between past and future may have been blurred or non-existent. The act of expansion, of magnifying quantum probabilities into concrete realities, could be what crystallized the flow of time as we experience it. The origin of time itself remains one of physics' most profound mysteries, but through the lens of inflation and entropy, we begin to see how our flowing, directional reality might have condensed from a state of timeless potential. This thermodynamic perspective weaves the story of cosmic birth into the irreversible narrative of time, adding a crucial layer to our understanding of why the universe is the way it is. The human drive to explain our origins, however, is as old as civilization itself, and the theory of inflation sits within a long and fascinating history of creation myths. Einstein himself initially resisted an expanding cosmos. When his own theory of general relativity predicted a dynamic universe, either growing or shrinking, he found the idea so distasteful he introduced a fudge factor, the cosmological constant, to force a static and eternal model. He would later call this his greatest blunder. The true turning point came in the 1920s with Edwin Hubble's meticulous observations of distant galaxies. He found a stunning correlation: the farther away a galaxy was, the faster it appeared to be receding from us. The universe was not static at all, it was stretching, and had been for billions of years. This discovery shattered the old paradigm and ushered in the era of the Big Bang theory, a cosmos with a definite, fiery beginning. Yet for decades, a rival idea persisted: the steady-state theory. Proposing that the universe had no beginning and would have no end, it suggested that matter was continuously created in the voids left by expansion, maintaining a constant average density forever. This elegant, eternal model held sway for a time, but it could not withstand the evidence. The discovery of the cosmic microwave background radiation in 1965 was a death knell for steady state, a clear, cool remnant of a hot, dense past that only a Big Bang could explain. But as we've seen, the classic Big Bang had its own deep flaws: the horizon and flatness problems. These were not minor issues, they were cracks in the foundation, hinting that a crucial piece of the story was missing. The stage was set for a revolution, one that would merge the world of the impossibly large with the realm of the vanishingly small. The 1980s saw particle physicists turn their gaze to the cosmos, bringing with them ideas of grand unified theories and scalar fields. It was in this fertile ground that Alan Guth planted the seed of cosmic inflation, a mechanism of exponential expansion in the first fraction of a second. His insight was immediately recognized as a potential solution, but his initial model was flawed. This sparked a period of intense creative ferment. Andrei Linde in the Soviet Union, and independently Paul Steinhardt and Andreas Albrecht in the United States, raced to refine the theory, developing the slow-roll version that provided the graceful exit. In a different approach, Alexei Starobinsky in Russia had already been working on a model driven by quantum corrections to gravity that also produced an early burst of expansion. The debates were sometimes heated, the competing models numerous, but through this collaborative and contentious process, a robust, testable theory emerged. This historical journey from a static cosmos to an inflationary one is a powerful lesson in how science truly works, not as a steady accumulation of facts, but through dramatic shifts in perspective, driven by a blend of mathematical insight, experimental evidence, and human perseverance. This entire edifice rests upon a beautiful and profound physical principle, the breaking of a fundamental symmetry. The elegant simplicity of the early universe was a symmetry of unimaginable power. For a fleeting moment, all of reality was governed by a single, unified force. This profound symmetry is the hidden engine behind cosmic inflation, a concept physicists call symmetry breaking. Imagine a perfectly round pencil balanced on its tip. This state is symmetric, identical from every direction, but it is also unstable. The slightest breath of air will cause it to fall, breaking that perfect symmetry as it lands pointing in one specific direction. The early universe underwent a similar cosmic fall. Grand unified theories propose that the electromagnetic force, the strong nuclear force that binds atomic nuclei, and the weak nuclear force responsible for radioactive decay were once a single super force. As the universe expanded and cooled, it crossed a critical energy threshold. This triggered a phase transition, a cosmic version of water freezing into ice. The single, symmetric force broke apart into the distinct forces we recognize today. This breaking of symmetry did not happen quietly. It released a tremendous amount of latent energy, and it is this energy that many models suggest powered the Inflaton field, driving the violent exponential expansion of space. We see a smaller-scale version of this process at work in our own universe today. The Higgs field, which gives particles their mass, operates on the same principle. It is a scalar field that permeates all of space, and its symmetry breaking is what distinguishes the electromagnetic force from the weak nuclear force. The Inflaton field is thought to be a similar but far more powerful cosmic cousin. During inflation, the universe was trapped in a symmetric but unstable state known as a false vacuum. Think of a vast flat plateau high in the mountains. This is the symmetric state, the false vacuum where the Inflaton field held a high energy value, driving the relentless expansion. But this plateau is not the lowest energy state. There is a valley far below. The end of inflation was the moment the field finally found a path downhill, breaking the symmetry of the plateau and rolling into the true vacuum of the valley, releasing all its stored energy to reheat the cosmos. This elegant framework does more than explain the mechanism, it makes testable predictions. The specific way the symmetry broke, the shape of that energy landscape, would have imprinted itself onto the quantum fluctuations. Searching for tiny deviations from a perfect Gaussian distribution in the cosmic microwave background, subtle signs of non-Gaussianity, is like looking for the unique cracks in a fallen pencil. They are the fossilized remnants of the symmetry breaking event itself. This powerful lens connects the behavior of the smallest particles to the grandest scales of the cosmos, revealing a deep and beautiful unity in physical law. To truly grasp the power of this process, we must listen to the language it was written in, the universal mathematics of fields and energy. The mathematical heart of inflation beats with two powerful rhythms, the curved geometry of general relativity and the probabilistic dance of quantum field theory. These two pillars of modern physics, one describing the cosmos on its largest scales and the other on its smallest, are woven together into a set of governing equations. The Friedmann equations, derived from Einstein's theory, dictate how the universe expands under the influence of its energy content. During inflation, this energy is dominated by the potential energy of the Inflaton field, a term that acts like a cosmic accelerator pedal, forcing the scale of the universe to grow at an exponentially accelerating rate. Meanwhile, the behavior of the Inflaton field itself is described by the Klein-Gordon equation, which is essentially the quantum field version of a simple harmonic oscillator, but rolling down the slope of its potential energy hill. The steepness of this hill is everything, and it is measured by two crucial numbers known as the slow roll parameters, epsilon and eta. Epsilon tells us how flat the top of the hill is, governing the rate of expansion, while eta describes the hill's curvature, which determines the mass of the Inflaton field and how long inflation can last. For inflation to persist long enough to solve the horizon and flatness problems, this hill must be incredibly flat, meaning both epsilon and eta must be much less than 1. This delicate, slow roll is what allows the universe to stretch so dramatically while laying the groundwork for its own end. As the field eventually rolls faster, the slow roll parameters approach 1, and inflation gracefully concludes, transferring its energy into the hot soup of particles. From this elegant mathematical dance, we can derive the most crucial predictions. The quantum jitters in the Inflaton field, when stretched by expansion, produce a specific pattern of density variations known as the scalar power spectrum. The steepness of the potential hill directly imprints itself on this spectrum, predicting the slight deviation from perfect scale invariance that our telescopes have now measured. Simultaneously, the same violent expansion ripples the fabric of spacetime itself, generating a background of primordial gravitational waves whose strength is given by the tensor power spectrum. The ratio of the tensor to scalar power, the famous tensor to scalar ratio R, is a direct probe of the energy scale of inflation. A detection of R would tell us the incredible height of that energy hill, linking our cosmic history directly to physics near the Planck scale. To navigate the complexities of reheating, where the Inflaton field decays in a turbulent burst, cosmologists turn to powerful numerical simulations. These computer models solve the non-linear equations as the field oscillates at the bottom of its potential, tracking the resonant production of particles that filled the universe with matter and radiation. This mathematical framework is not just abstract beauty, it is a precise language that allows us to test our cosmic origins against the cold, hard data of observation. Every measurement of the cosmic microwave background is a test of these equations, a check on the specific shape of a potential energy function that existed for a fleeting moment at the beginning of time. This profound connection between abstract mathematics and tangible reality raises a deeper question about our place in the cosmos. As we grasp the very equations that govern creation, what responsibility does this knowledge bring, and how does it shape our view of humanity's role in the universe? Grasping the reality of cosmic inflation can feel like stepping back from a single grain of sand to behold the entire beach. Our entire observable universe, every galaxy and quasar, is the magnified imprint of a subatomic speck. This realization carries a profound philosophical weight, shrinking our earthly dramas to a breathtakingly small scale, while simultaneously elevating the human mind that managed to trace this epic story. We are not the center of the universe, but we are a way for the cosmos to begin to understand itself. This cosmic perspective, born from the evidence for inflation, challenges the ancient instinct that we hold a privileged place in creation. Instead, it invites a quiet humility, a recognition that we inhabit a fragile world orbiting an average star in a remote corner of a galaxy that is itself just one among countless billions. Yet this is not a story of insignificance but one of connection. The same quantum fluctuations that seeded the great cosmic web are the reason you exist to ponder them. The calcium in your bones, the iron in your blood, was forged in stars that could only form because of that primordial blueprint. We are not just living in this universe, we are a literal part of its inflationary legacy, stardust that has become conscious. This grand narrative is also a powerful testament to human collaboration. No single person or nation uncovered this story. It was built through decades of work by theorists and observers across the globe, from the radio astronomers who first heard the cosmic microwave backgrounds hiss to the international teams that built satellites and supercomputers to decode its message. While you will not find a direct application for the Inflaton field in your daily life, the relentless pursuit of such fundamental questions consistently drives innovation. The technology developed to measure the faint whisper of the Big Bang finds its way into medical imaging, data transfer, and materials science, enriching our world in unexpected ways. Sharing this story, fostering a society that values curiosity and evidence-based reasoning, is perhaps one of the most practical outcomes of all. It reminds us that our greatest asset is not what we know, but our endless capacity to ask what lies beyond the horizon of our current understanding. This human quest to comprehend the cosmos from the first moment to the last is a continuing journey, and just as inflation set the initial conditions for our universe's birth, it may hold hidden clues about its final destiny. The same force that crafted our cosmic beginning may also be scripting its final act. The universe's initial, violent acceleration and its current, gentle one are two bookends of a single, sprawling narrative. This story connects the Inflaton field, which powered the Big Bang's prelude, to the dark energy now pushing galaxies apart. If dark energy is not a simple constant but a dynamic field called quintessence, it could be a faint echo of that primordial engine, slowly evolving even today. Such a field would not just accelerate expansion, it could alter its character over billions of years. A gentle quintessence might lead to a heat death, a slow and cold fading where the universe expands forever, stars burn out, and matter itself decays into a dark, dilute void. But a more potent, growing form of quintessence could lead to a far more dramatic end, the Big Rip. In this scenario, the repulsive force of dark energy becomes so overwhelming that it overcomes all other forces. First, galaxy clusters would be torn asunder, then individual galaxies. As the end nears, stars are ripped from their orbits, planets from their suns. In the final moments, atoms themselves would be shredded, and the very fabric of space-time would be torn apart. This ultimate fate hinges on the equation of state of dark energy, a single number that measures its pressure and density. Our current measurements suggest a value very close to that of a cosmological constant, pointing toward a gradual heat death, but the door remains open for a more dynamic and destructive quintessence. Beyond the fate of our own pocket of reality lies an even grander picture: eternal inflation. If this is correct, then the meta-universe, the greater background reality, continues to inflate at a fantastic rate forever. Within this eternally churning foam, countless bubble universes like our own are constantly being born, each with its own laws and its own destiny. Our universe will eventually grow cold and dark, or perhaps be torn to pieces, but the greater inflationary cosmos is immortal, a perpetual engine of creation. This grand cycle raises a profound possibility that the universe is not linear but cyclic. Some models suggest that the dark energy diluting our cosmos could eventually transform, seeding a new inflationary epoch that leads to another Big Bang. In this view, the end of one cycle becomes the beginning of the next, an infinite, rhythmic dance of birth, death, and rebirth. The story that began with a quantum tremor in a microscopic patch of space may ultimately dictate whether our cosmos faces a silent eternity or a violent dissolution, or if it is merely one verse in an endless cosmic poem. This entire edifice, from the first fraction of a second to the final state, rests upon a foundation of evidence. The evidence for cosmic inflation weaves together a tapestry of independent clues, each strand reinforcing the others into a formidable case. Large-scale observations reveal a universe of startling uniformity, a smoothness that stretches across billions of light-years. This vast cosmic evenness finds its perfect partner in the geometry of space itself, measured to be exquisitely flat, balanced on a razor's edge. These two facts alone point to a primordial smoothing and stretching event, but the proof goes deeper, etched into the oldest light we can see. The specific pattern of hot and cold spots in the cosmic microwave background is not random noise. It is a near-perfect match for what inflation predicts, a nearly scale invariant spectrum of fluctuations where the relative strength of the ripples is almost identical, whether you look at a small patch of sky or a large one. These primordial seeds were also adiabatic, meaning the ripples in matter and radiation were perfectly in sync, a coordinated dance that only a rapid, smooth expansion could have orchestrated. Beyond this ancient light, the very structure of the cosmos testifies to an inflationary past. The grand cosmic web of galaxies and voids, mapped in stunning detail by sky surveys, grew directly from those tiny quantum jitters amplified to cosmic proportions. The statistical properties of this vast network, the way galaxies cluster and voids are distributed, align precisely with the initial conditions laid down by inflation. And the theory even solves mysteries by explaining absences. Where are the magnetic monopoles? These bizarre, isolated magnetic poles are predicted by many grand unified theories, yet we have never found one. Inflation provides the elegant answer, diluting these relics to such an undetectably low density that encountering one would be a cosmic miracle. The cumulative weight of this evidence, from the smoothness of space to the blueprint of galaxies, has cemented inflation as the standard model of our universe's first moments. While the direct detection of primordial gravitational waves remains the final, elusive prize, the indirect case is already overwhelming. This body of support is why the scientific community takes the theory so seriously, viewing it not as a wild speculation but as the most compelling narrative that fits the data. Yet for all its successes, this is not the end of the story. The very strength of the evidence now pushes us to confront the deeper, more perplexing questions that inflation itself cannot answer. The Inflaton field remains a ghost in the machine, its fundamental identity a secret the universe has yet to surrender. We can trace its breathtaking effects across the sky, yet we do not know what this field actually is or why it was poised to begin its monumental role. This is the first great unresolved mystery. The initial conditions for inflation present a similar puzzle. The theory brilliantly explains why the later universe was so smooth and flat, but it requires its own finely tuned starting point. Why was that primordial patch so perfectly uniform and energetic, ready to trigger the entire cosmic chain of events? We have pushed the question of a beginning back one step, but we have not answered it. These mysteries are compounded by our incomplete understanding of quantum gravity. Inflation paints its picture on the canvas of classical spacetime, but in the very first instance, that canvas itself was a seething quantum foam. We lack the final theory that describes this realm, leaving our story of the absolute beginning frustratingly blurry. The path forward hinges on a critical test, the hunt for primordial gravitational waves. Detecting their faint swirl in the cosmic microwave background would be a direct message from inflation's violent energy scale. Conversely, if next-generation experiments find nothing, it would force us to discard many of the most popular inflationary models and perhaps rethink the entire paradigm. This search is not just about confirming a theory, it is about ruling out entire universes of possibility, another deep puzzle is the origin of everything we see. Our universe is made almost entirely of matter with very little antimatter. This fundamental asymmetry, known as baryogenesis, should not exist if the Big Bang had created equal amounts of both. The solution may be woven into the end of inflation. As the Inflaton field decayed and reheated the cosmos, its specific interactions could have violated key symmetries, preferentially generating more matter than antimatter. This process, potentially through a mechanism called leptogenesis, suggests that the very stuff of our existence is a relic of inflation's final, turbulent moments. Even more profound are the problems that emerge if eternal inflation is correct. The multiverse concept offers an explanation for our universe's fine-tuning, but it introduces the daunting measure problem. How do we calculate probabilities in an infinite ensemble of universes? If everything that can happen does happen somewhere, then the concept of what is likely or unlikely seems to lose all meaning, challenging our ability to make any testable predictions at all. Then there is the cosmological constant problem, perhaps the most glaring discrepancy in all of physics. Our observations show that dark energy is incredibly feeble. Yet when theorists calculate the expected energy of the quantum vacuum, the result is a value some 120 orders of magnitude larger. This is the worst prediction in the history of science, a staggering void between theory and observation that suggests we are missing something fundamental about the nature of empty space itself. These are not failures of inflation, but the frontiers where the next great discoveries await. Resolving them will require a dual assault, with next-generation telescopes like the Nancy Grace Roman Space Telescope and the Vera C. Rubin Observatory mapping the large-scale structure of the universe in unprecedented detail, while gravitational wave observatories like LISA listen for the faint hum of the cosmic dawn. The journey to understand our origins is far from over. The biggest revelations are still hidden, waiting in the subtle patterns of ancient light and the quiet ripples in space-time, promising to rewrite our story once more. From a mysterious burst of hyper-expansion to the intricate cosmic web we observe today, this journey has reshaped our very conception of reality. We have followed the evidence from the faint afterglow of the Big Bang, traced the quantum seeds of galaxies, and confronted the ghostly Inflaton field and the possibility of a multiverse. Though profound puzzles remain, this framework connects the tiniest quantum jitters to the grandest structures in existence. Our quest to understand what powered the universe's rapid expansion continues, driven by ever more powerful telescopes and brilliant theoretical insights. The universe's story is far from finished, and each new discovery reveals deeper layers of wonder. If this exploration of cosmic beginnings ignited your curiosity, we would love to hear your thoughts in the comments. For more voyages to the edge of understanding, subscribe and join us as we continue to unravel the greatest adventure of all.